All right. Okay, well, here we are. We're standing in the teaching lab right now where the lasers are, and I guess you can recognize some familiar faces. And the person holding the phone is Kifang. Um, so, uh, so what we're going to do is try and show you, what the lab was. And it says building an external cavity tunable diode laser system. So just think of that as building a diode laser system for now. And all the rest of the words in there are to be able to make a laser system that can actually measure hyperfine structure of the atom. So something that is extremely frequency tunable and also extremely narrow bandwidth. So we have to take the bandwidth of the commercial laser and really narrow it down. But anyway, in this lab, all we want to do is fire it up, meaning get some light output from it. And then we want to show that the light, which is highly divergent coming out from the laser, it needs to be collimated. And then we also want to make some comments about the polarization. Now, we're not going to fire up the laser really today, but I just want to show you what's involved, what are the components. Okay, so let me set this down here for a moment. And I will be sending this manual to you today. Please listen to this video while keeping the manual in front of you. I think it would be a good idea. All right, well, so let me first show you what the laser looks like. So here are a couple dead lasers. Now it says in the manual, do not touch the laser, because the moment you touch it, there is enough electrostatics on your body to kill it. Now these guys are already dead, so we can have our way with them. It's fine. And these are two different kinds of lasers that you see. These are two different packages. There is a 9mm package, and there is a 5mm package. That's what they're called. And the the output, it's easier to show on this guy, that the output shoots out from the top. It's a diode, so there are pins below, and for a diode you would have expected two pins, an anode and cathode, and that's exactly what two of the pins are. The third pin serves a monitor function. Okay, so I don't know if is it showing up in the light clearly, but I hope you see three pins there. You see, and two of the pins are the anode and diode. Anode and cathode is what I meant. Okay, and maybe you can see it. And this is by the way, the laser that you'll use. Once again, you see the output comes out from the top right there. And then you see how this has slightly longer pins. And remember, it's dead, right? So we can do whatever the hell we want with it. And you see three pins there, right? Okay, so two of them are anode and cathode. So this laser, and so we need to supply current to it in order to make it work. Okay, and the current is going to be supplied from these. There's a diode controller. It goes up to 200 milliamps, which is way more than we need. But anyway, we'll use this guy for the current. And then there's also another guy who does the temperature control, because it turns out that the frequency of the light coming out is extremely sensitive to the temperature. You have to hold the temperature constant to less than like a fraction of 0.1 degrees. 0.1 is too much, actually. I mean, like, you want to keep it to 0.01 degrees for sure, at least. Okay, so this laser is going to be stuck into an aluminum mount, just because the laser has to be held somewhere. And so, and I'll, everything you see here has a purpose, so that brown dot there is actually, there's a reason for it. And also the white goop that you see on top has a reason for it. That's a temperature, a thermal contact. It gives you good thermal contact. So there's something that's going to be affixed on top here. But anyway, don't worry about it right now. Here's the laser, and it just slides right into that, you see. And the two holes on the sides are to house two screws that will keep the laser firmly mounted inside. And on the other side, the face is supposed to be pushed right up against the output, like that. You see how it came right up against the output, the output face of the thing. So it's got to be screwed in and held there, okay? And then it's placed on top of this aluminum base. Now you will read in the manual, so let me just set this down for a sec. You'll read in the manual that, this laser has to be made extremely stable. And so one of the things you have to do is safeguard against vibrations. So you can't just place the laser on the table and start to work. Even there's stuff on the table that vibrates in many experiments. So you want to put the laser on its own little base plate, and we're using this aluminum base plate. On this aluminum base plate, you will put down this sorbethane rubber, which is isolates you from vibrations on the table. On that, you put this base plate, the big base plate. That was the big base plate. This is the base plate on which the laser would go. So here's the laser right inside its mount, and it sits on this end of this base plate. Now you'll notice that this base plate looks kind of funny. And as you read in the manual, you'll see that the base plate has been chopped partially to make an aluminum arm, which can be tuned slightly away or toward the rest of the plate using this fine pitch screw. So just by turning this fine pitch screw clockwise or anti-clockwise, you can make this arm go away or toward quite sensitively. And the one precaution you always have to take care of is that you never turn the screw so much that this arm gets flexed out too much, because then it won't come back, because after all it's an aluminum elbow, right? So it's meant for ultra fine sort of positioning, but you don't overdo it, okay? So here's what happens. This goes on top of the sorbethane, okay, like that. And so there. And then the laser, which is inside here, it needs to go on the plate. But remember, the laser is an electrical device. We are going to want to temperature control it. So we want to, you can easily temperature control about this much mass. So you want to isolate it thermally and electrically from the rest of the base plate, okay? And this plate, of course, is thermally and electrically isolated from the rest of the stuff because of the sorbethane. But here's a Teflon spacer. It's mentioned in the manual, which is placed below this. And then, it's all screwed down into those two holes like that. So that's where the laser will sit. It's thermally and electrically insulated from all the rest of the stuff. And in order to temperature control this, we are going to use something called a thermoelectric cooler. That's the white thing here. So I think it's slightly, that's this guy, okay? It's a thermoelectric cooler. If you supply electricity to this, one of the plates becomes hot, the other cold, okay? And so in this case, the cold plate is attached to, let me just first do this. Let's move these guys away. So the cold plate is attached onto the laser block, okay? And it's all going to want to move right now, so I'm going to put my hand, oops. So anyway, this with the insulation, let's say if one can reach across and just hold this down with it. So it'll stay on there. And then you have to put a heat sink on top, because when it cools the aluminum mount, the other side gets hot and it needs to be cooled by air. So we apply this cooling fin on top like that. okay? And so that makes the setup for your laser. All right, so I'm going to remove this so that you can see. Now the laser, of course, is, just fell right out, but the laser, which is inside this mount, is shooting light out in that direction. And the first thing that you notice is that it's extremely highly divergent, okay? And so you have to collimate it. And so there's a lens, and this lens is like a $300 lens. So you have to be very careful with it. There's a lens in there, okay, with a very short focal length. Right, what you're seeing is the coating on the lens. That's the color that you see. And so I'm just gonna put this inside here. You see it's inside the mount, and I lock it down, and then the lens, and now if you can bring it right on top there, if you can see from the top, the whole point, so you see now the lens is brought in close to the laser, and now you see how the arm helps you, because that lens needs to be exactly its focal length away from the laser. You've learned in class that the laser is extremely spatially coherent, so it's like a point source, and so this lens is able to take that point source and the highly divergent light. It needs to be really close so that it can capture all the light coming out from the diode, and then you get a collimated output here. And the first lab is about positioning this lens carefully in front. You have to vary that distance so that it becomes exactly what the focal length is, so that you get a beam that neither diverges nor converges out to at least about 8 or 10 feet. Okay, maybe the end of so right where the door is in this case. All right, and you do realize this table where it's oriented. I hope you've been able to figure that out. How are we going to make this laser narrow bandwidth? Because I think in class I've mentioned this, and it's important to know that the frequency bandwidth of the light coming out from the laser is on the order of anywhere from it's on the order of 10, it's on the order of a gigahertz or more, okay? So anywhere from 1 to 10 to 100 gigahertz, that's the frequency bandwidth. And you have to narrow it. How much do you have to narrow it? Well, you have to narrow it down into the megahertz or the kilohertz range. So that's a huge reduction. I'll tell you why you have to do megahertz or kilohertz reduction when we do the lecture. But how do we do that? And the component we're going to use is this diffraction grating. And I hope you can see how it's a diffraction grating, right? You get the light being, you see how the colors are being reflected off that diffraction grating. So we're going to take this diffraction grating and station it in front of the laser, okay? And this is something that we will talk about later, but we'll use this diffraction grating to make the output of the light narrow bandwidth, okay? And that's a subject for the next lab, so I'm not going to talk about it right now. All right, so I'm just going to let this guy sit here like that. Just let it perch. Wants to keel over. Hey, Ian, can you just keep your finger on here at the back?
I got it.
Yeah, just to, okay. Yeah, just to prevent it from tipping over.
Yes.
And the final component in this laser system is, it turns out that you want to couple light out. There is some light coming out, but you want to couple light out in a certain manner. So there needs to be a beam splitter that you will place in. And this beam splitter is just like the one you used in your Michelson interferometer. And you have to place this beam splitter in there, so that right in the path of the light between the diffraction grating and the lens, so that as you can see from the beam splitter, light will come out this way. and that's the usable light for your experiment. Okay. So this was the first lab, and Ian and Kifeng are going to set this system up, to give a laser beam that is collimated. And we will, first in the first lab, actually, what we're going to do is, so we're going to remove this. We're not going to do that. We're not going to do this. We're just going to set this part up. Okay? We're going to have a collimated output. We're going to show you that the beam looks like an ellipse. And this is something I'll talk about in my next lecture, that the beam looks like an ellipse. And why is that? Why does it look like an ellipse? And the other thing that we'll talk about is that if the ellipse is, let's say the long side is horizontal and the short side is vertical, then it turns out that the light is always polarized. For this configuration, it's polarized vertically. So it's always the direction of the short axis is the direction of the polarization of the light. And why is that? So these are the two questions that I will discuss in my next lecture. And this is the first lab that these guys will be building. There will be no other video or lab this Thursday, because I have to go and actually pick up my daughter from Connecticut. Yale has shut down its research operations, and I imagine that may happen at Miami soon also. But anyway, so nothing this Thursday, then that gives me spring break to get organized a bit better. And but I will post lectures, and there will be a short quiz. So now let's see how big this file is, because I've been yabbing for like some time here. I thought it will be a 5-minute video, but it's way longer than that. So
17 minutes already.
17 minutes, and so we'll see how many gigabytes that is, and so live and learn. Okay, so keep rowing, stay healthy. Talk to you soon.
Okay.